Good morning, everybody. All right, notes 2. So we learned about the different parts of a chemical reaction. Now we're going to learn about this idea of balancing chemical equations and reactions. So 2 major goals in this video. Number 1, just reviewing and making sure we understand the law of conservation of matter or mass, which in reality is the reason why we balance equations. All right, and then the idea of balancing equations itself. All right, so again, make sure you're taking notes. If you've got any questions, please bring those up in class. All right, first idea that we need to understand is the law of conservation of mass or matter. All right, the law of conservation of mass or matter states that matter, which as a reminder is anything that has mass and takes up space, cannot be created or destroyed. Okay, we generally say that it can be transformed or transferred. Okay, so law of conservation of mass, matter cannot be created or destroyed. So what does that actually look like? All right, so if we're actually looking at a chemical reaction here, if we zoom in, all right, looking at the different parts. So this is the combustion of methane. So you've got methane reacting with oxygen to form carbon dioxide and water. All right, if we were to break it down to individual molecules and or atoms, all right, you take a look here, you see that there is 1 carbon atom on the reactant side, 1 carbon atom on the product side. You see that there are 1, 2, 3, 4 hydrogen atoms on the reactant side. 1, 2, 3, 4 hydrogen atoms on the product side, and then you see 1, 2, 3, 4 oxygen molecules on the reactant side, and 1, 2, 3, 4. So the same number of atoms that we began with, we also ended with, we just happened to rearrange them. In addition, the other way we can identify this, and this tends to be the way that we do this in class because we can't see individual atoms, is by taking quantitative data of mass. All right, so if I come down here, if I start with 16 grams of methane and roughly 64, because each oxygen molecule weighs 32 grams, I start with 80 grams of matter on my reactant side. All right, when I create my new products of carbon dioxide, I have 44 grams of carbon dioxide, 2 water molecules, each 18 grams. I end with 80 grams. All right, so what we should see when even though we cannot see individual particles or atoms, is that what I start with is what I end with in terms of mass. All right, so here you can see the mass of the reactants is always going to be equal to the mass of the products when I run reactions. Okay, that is our evidence for the law of conservation of mass. All right, if I do not have equal mass at the end, then I have to question whether or not that reaction fully occurred, if I might have produced gas and maybe I didn't measure gas at the end, if something escaped, etc. All right, which leads us to this idea of balancing chemical equations. All right, balancing just really means to make sure that our reaction or our equation is following the law of conservation of mass. All right, otherwise we're violating it, and we know if it's a law that it's been proven over and over by multiple pieces of evidence. So rather than giving you a step-by-step guide here, we're just going to kind of show you through examples how to do this. All right, so this is a reaction between potassium and chlorine to produce potassium chloride. All right, the first thing I'm going to have you do is find that arrow. So if we zoom in here and we find the arrow, and I'm just going to draw a line that separates my reactants and products. Now, according to the law of conservation of mass, I have to have the same number of atoms in the beginning as I do in the end, although they might be rearranged. So I'm going to break this down and make a list of the atoms that I have. So on the left-hand side, I know I have potassium and I have chlorine, and I see that I also have potassium and chlorine on my product side. Now I'm going to count how many of each atom I have. So if I look at potassium, right, there's no subscript, so I assume 1. If I look at chlorine, it has 2 atoms of chlorine in that molecule. If I come over to my right-hand side, there's no subscript, so I assume 1. If I look at chlorine, no subscript, I assume 1. All right, when I see this, I should notice that on the left-hand side, there are 2 chlorine atoms, and on the right-hand side, there's only 1, which means somehow I lost matter. That violates the law of conservation of mass. That cannot be true. So I'm going to have to put in coefficients, right, to balance this chemical reaction. So when I do this, I'm just going to draw a line in front of each of these because I know coefficients go in front of these. All right, so if I have 2 chlorines atoms on the left and I only have 1, I'm going to put a coefficient of 2 in front of potassium chloride. Now, when I do this, this 2 not only applies to the chlorine, but it also applies to the potassium. It kind of distributes itself. So I now have chlorine with 2 atoms. Check. That is now following the law of conservation of mass. But now I also have 2 potassium atoms. All right, now I'm going to have to go back to the reactant side. Is there a coefficient that I can put in front of potassium to make sure that it's following the law of conservation of mass? Yes, I can put a coefficient of 2 here. And if I do that, now I have equal amounts of each atom on the reactant and product side. Now notice I don't have a coefficient in front of chlorine. We always assume 1 if there's nothing written. If you need to write that 1 to help you out, that's totally fine. Okay. Let's do another example. All right, so for this one, we've got aluminum and oxygen reacting to form aluminum oxide. We're going to follow these same steps, so I'm going to divide this up to my reactant and my product side. I'm going to make a list of my elements. So I've got aluminum and oxygen. I would also make sure when you make these lists that they look the same on each side so you don't mix them up on accident. All right, I have 1 aluminum on my reactant side, and I've got 2 oxygen atoms on my reactant side. Over here on the product side, I've got 2 aluminums, and I've got 3 oxygen atoms. All right, clearly a violation of the law of conservation. I've gained aluminum and oxygen somehow, which we know cannot happen. So I'm going to have to go back and put in coefficients, all right, to get this balanced. Now, this is kind of an example when we're going to look for, and sometimes this happens with oxygen and hydrogen, common multiples. Okay, so what I mean by that is I have 2 oxygens on the left, and right now this is a coefficient of 1. Right, so if I try to put this as a coefficient of 2, that now gets me 4 oxygens versus 3 on my product side. That's still not it. All right, so I might delete that, and I might try to put 3 in. All right, that gets me 6. And I go, my gosh, I'm getting further and further away. Let me check the other side. Oxygen has 3. Well, I can't put, I can't add these, so maybe I make this also 6, and what's times 3 equals 6 is 2. All right, so I tried to find a common multiple 2 on numbers that both of them go into in order to get those oxygen elements equal on each side. All right, now when I do that, remember that this coefficient also applies to aluminum, so now that changes aluminum to 2 times 2, that's 4 aluminums on my reactant side. So I'm going to have to come over to, my product side. I'm going to have to go over to my reactant side and put a 4 here to make this 4. All right, now I have equal amounts of aluminum on my reactant side as on my product side. We're just going to do a few more, and I'm going to give you a few more tips when you look at these, some methods. All right, this does take some practice. It's kind of like a little puzzle. All right, this one's getting a little bit more complicated. We're going to see all of a sudden that we put in some polyatomic ions. Remember, a polyatomic ion is a series of nonmetals bonded covalently that carry a charge. So you see those with iron hydroxide as well as potassium hydroxide here. So there's a lot more elements here. So now I'm going to kind of introduce you to something called the minnow method. So I'm going to come over here. Sometimes you don't know where to start. Which element do I know to balance first? And if I start with the wrong one, it makes it more difficult. So we have something called the minnow method, and it's not at all something you have to do, but it kind of gives you a checklist of, okay, I've got those taken care of, okay, I've got these taken care of. So M stands for metals. So you'll start by looking at metals. As a reminder, metals are anything to the left of that staircase. All right, then you've got polyatomic ions is your next one. All right. Then you'll check all of your N is for nonmetals. And then we're going to end with O is for oxygen, H is for hydrogen. Now, I know oxygen and hydrogen are nonmetals, but those tend to be the ones that get people stuck. And if you can do your metals, your ions, and your nonmetals first, it tends to make balancing oxygen and hydrogen easier. So let's still use our steps that we did before, but we'll also use this minnow method here. All right, so I'm still going to start with drawing a line where my arrow is to separate my reactants and products. And I'm also going to start by listing all of the elements that I have here. So I've got potassium, I've got bromine, I've got iron, and I highly recommend that if you see your polyatomic ion on one side and it stays together on your product side, that is how you list it. So you've got hydroxide versus separating the oxygen and hydrogen. All right, I'm going to list these the same way, in the same order on my product side. Okay, now it's time to count. On my reactant side, I've got 1 potassium, I've got 1 bromine, I've got 1 iron, and I've got 3 hydroxide ions. If I come to my product side, I've got 1 potassium, I've got 3 bromine, 1 iron, and 1 hydroxide. Remember, if it's not listed, you assume 1. All right, so let's go through minnow method. Metals. So potassium and iron are my metals. So if I look at potassium, I've got 1 potassium on my reactant side, 1 potassium on my product side. That's balanced. All right, do I have any other metals? I do. I have iron. All right, I see on my reactant side 1 iron, on my product side 1 iron. Okay, all metals done. Check. The next one says polyatomic ions. Okay, I've got 3 hydroxide on my reactant side, 1 on my product side. That means I'm going to have to put in a coefficient. So I'm going to draw my line. I'm going to have to put a 3 here to make sure I get 3 hydroxides. Now, by doing that, I have balanced my hydroxide ions, but I have now changed potassium to 3, which is okay. Now I just go back and I have to make sure I put a coefficient of 3 in front of potassium. Okay. All right, no more polyatomic ions. The last thing I have to check is non-metals that are not oxygen and hydrogen. I do have bromine. Over here on the left-hand side, since I put the reactant side up a 3 in front of potassium, that makes bromine 3. And I happen to have 3 bromine on my product side, so I am done and checked. And as a reminder, you don't have to do this. You can leave these blank, but if you want to put coefficients of 1 to help you out, to know that you're finished, that's fine too. Okay. All right, in our last example here, this is actually an example of a combustion reaction. I'm going to change this one a little bit because this one's really hard. We're going to change this to a 6 and a 12 here. Otherwise, this gets real rough. Okay, so combustion reaction, you're always going to see just carbon, oxygen, and hydrogen present, and you're always going to see carbon dioxide in water form. We're going to follow the same process, all right? When you're doing combustion reactions, I would always start with carbon, then hydrogen, and then oxygen when you're balancing, just because the oxygen can get kind of complicated. So if you start and do that one last, then it tends to get balanced on its own. So if we go through here, let's take a look. On our reactant side, we've got 6 carbons. On our product side, we have 1. On our hydrogen side, we've got 12, or on our reactant side, we have 12 hydrogens. On our product side, we've got 2. right, and this is where it can kind of get complicated here. On the left-hand side, we've got 2 oxygens. On our product side, we've got carbon dioxide that has 2, and we've got oxygen that has 3, right? Because it's coming in 2 different compounds. It's in the carbon dioxide and water, which is why it can get complicated. So let's just start with carbon and see where we end up. All right, if I've got 6 on my reactant side, I'm going to come over here, and it probably makes sense, we'll kind of change color here so we can see this, to put a 6 in front of the carbon dioxide here. When I do that, that changes carbon to 6. Now, let's just be careful. So over here, that changes, we'll do the oxygen later, but notice it will affect the oxygen. All right, on the reactant side, I've got 12 hydrogen, all right, and I only have 2 on the product side. So I know that 2, if I multiply by 6, gets 12, so I'm going to put a 6 here. All right, if I do that, that gets me 12 hydrogen, and that gets my carbons and my hydrogens balanced. All right, now I have to do total oxygens. Let's see how it shifted. All right, so here I've got 6 times 2. That's 12 oxygens for my carbon dioxide. And I've got 6 times 1. That's plus 6 more oxygens on my water. So 12 plus 6, that gets me 18 total oxygens on my right-hand side. All right, well, if I go over here, there's a 2. All right, so I'm going to have to put a coefficient. So what times 2 gets me 18? All right, so I'm going to take 18 divided by 2, and I get 9 here. Okay, so I get 1, 9, 6, 6 is going to get me balanced. That's going to get me 18, and now my oxygen is balanced. So again, so for combustion, you're still kind of following that middle method, but you're not going to have metals or polyatomic ions, so you'll start with your nonmetal carbon and finish with your hydrogen and your oxygen. All right, we'll definitely do some more practice in class, but here's just kind of your intro to starting your balancing chemical reaction.